Yes, this is my Python physics series. I'm not on Trinket. This is paper. Okay, so I don't want to freak you out. I'm starting on paper. But today what I want to do is nothing super new, but I want to model the motion of an object near a planet. I'm going to use planet Earth and make graphs of energy. Okay, and it's going to be fun. So let's just do a brief review. Suppose that I have some origin, and I'm actually going to put the Earth, it could be anywhere. So I'm going to call this vector R Earth. That's from the origin to the center of the Earth. And then I have some spacecraft. I'll put it over here. I'll call that location RS for spacecraft. I want to calculate the force on this object, the gravitational force. So my gravitational force, I need this vector R from, let's do it this way, from the Earth, call that R, where R is equal to R spacecraft minus R Earth. This is very useful, and I'm going to do this. I'm actually going to put the Earth at the origin, but I'm still going to do this because, actually I'll move the Earth a little off the origin. Because there's a lot of cases and a lot of problems where we're going to work on where you have to do this, right? And I think it's easy to start off with the Earth at the origin, just use the position of the spacecraft as R, but it's not always that way. Now I can calculate the gravitational force on the spacecraft. I'll call it Fg. As a vector, it's negative g, mass of the spacecraft, mass of the Earth, divided by the magnitude of r squared times r hat. So this is really important. The gravitational force depends on g, the gravitational constant, the mass of the Earth, spacecraft, which it doesn't really matter, the mass of the Earth, 5.974 times 10 to the 24th. But since I'm dividing by the distance squared, I need to take the magnitude of that distance and then square it. But then it's not a vector, so I need to multiply by the unit vector r hat. This is important. And this is the only force acting on this. Then I can say this has some momentum p, and then I can use my normal p F net, which is only gravitational force, is the change in momentum with respect to time, and p2 equals p1 plus f delta t. This is my normal numerical recipe. This is actually the Euler method. It's not the best, but it's so easy to use, and it works in a lot of cases that we're going to use that. And then I can update the position of the spacecraft. RS2 equals RS1 plus P2 over ms delta t. And I'll just keep doing that over and over again. But every time I move the position of the spacecraft, I need to recalculate the gravitational force. So that's what's going to be fun. Okay, now when we make a plot, I really want to plot the total energy. I'm going to make multiple plots. So I'm going to have the kinetic energy is 1/2 m. It would actually be this, p squared over, p squared, magnitude of p over 2m. And I'm doing it that way because I'm calculating the momentum, updating the momentum. I don't have to calculate the velocity that way. I can take the square, the magnitude of the momentum squared and divide by twice the mass, and that'll be the kinetic energy. And then the potential energy is going to be negative g ms me over r. And that's actually like this. And that would actually be rs. No, it's r. It's r. Okay, so let's jump over to Python and make this happen. Now, there's another important thing that we're going to have to deal with, and that's the time step. In projectile motion, we dealt with the time step of 0.01 seconds or something like that. But if this is moving at some large altitude, it's going to take hours to go around. And so if I put a small time step, it's just going to be crazy. I can make a much bigger time step because even if this is going 1,000 meters per second, in 1 second, it would only move 1,000 meters, which isn't actually too terribly far. Okay, so it's just an example. We're going to play around with the time step and see what happens. But let's jump over to Python and get started on this program. Computer, there we go. Okay, hello Python. And I'm going to give you the code. And just a quick reminder that this is my series on Python. It's not supposed to be super programming oriented, it's physics oriented. So I'm not going to do things the best way, and I'm fine with that. Hopefully you're fine with that too. Let's just start entering our constant, 6.67 times 10 to the negative 11th for G. ME is 5.97 times 10 to the 24th. RE is 6.37 times 10 to the 6th. That's all I need. Now the first thing I'm going to do is make the Earth. And I'm going back and forth, but I'm going to put the Earth at the origin just because it's easier that way. So let's say Earth equals sphere, position equals vector 0, 0, 0. And also in this case, I'm going to use a low mass spacecraft, and that means that the motion, the momentum of the Earth's not going to change. But we'll do that case later where the two objects both change. Radius equals RE, and let's just run it. There's my Earth. Okay, now again, that's a huge radius, but Python zooms in to make the whole thing so you can see the whole thing. So there it is. Now let's do this. This is one of my favorite tricks in Python. Texture equals textures dot Earth. Come on. So there's my sphere, and it's the Earth. Now, there are some problems here. Problem number 1 is that it's shiny. Problem number 2 is that there are more than one point sources, and you can fix that, and I will in a later video. I'll show you how to make a realistic Earth-Moon model system, and it'll be great. But for now, let's just go with the way it is. And I'm going to actually make my spacecraft orbit around the Earth this way. So remember that this is the Y direction. This is the X direction. So Z is coming in and out of the screen. Okay, let's. I could also do Earth.m and give the Earth a mass as a property of the object of the sphere, but I'm not going to do that. Let's call the spacecraft. Let's call it a craft, and it's also a sphere. And so the radius of the Earth is RE. I'm going to put it twice the radius away. So the vector, it's going to be equal to vector 2 times RE in the X direction, so it's that way. My screen's backwards. 0, 0. The radius, now you say, oh, it's spacecraft, so maybe a 10-meter radius would be big, right? But if I do that, you can't see it. I'm going to go ahead and do that. Equals 10. Let's make it yellow. And let's also leave a trail. So make trail equals true. And now I'm just going to run it. And then you can't see anything. See, it's there. You just can't see it. So let's make the radius, let's make it 20 times smaller than the Earth. So I can say RE divided by 20. Let's try that. There's my spacecraft, which is way too big. Okay, maybe make it a little bit smaller, just make it look cool. And it's a sphere. You can make it a box if you want to. But the problem with the box is that, how do you rotate that around? Remind me to rotate boxes later and show you how to do that. Okay, so now I'm going to need to put some properties in there. Let's say craft.m equals 1,000 kilograms. Craft.p, the initial momentum, I'm just going to say 0. Vector 0, 0, 0. I'm going to release it from rest. No, I'm not. I'm going to give it 1,000. 500. 500 meters per second in the Y direction. But I need to multiply that by the mass times craft.m. Okay, so now I need to set the time. T equals 0. dt equals, let's do 10. I'm just picking. I really don't know what it's going to be. And now I'm going to make my loop. While t is less than 1,000. So if I do 1,000 divided by 10, that would be, if I ran this at that's, let's see how many calculations that be. 1,000 divided by 10 would be 100 calculations. It's not that much. So let's put one more, 10,000. And let's do, remember the colon, a rate of 100. So that would do 100 of those every second. So take 10 seconds. I think that's right. Let's make that a little bit faster. 200. Okay. Now the first thing I'm going to do is calculate the vector r. And the r is a vector from the Earth to the spacecraft. So I can say r equals earth.pos minus craft.pos. Remember, earth.pos is the vector locating the center of the Earth, and craft.pos is the vector locating the center of the craft. Now, in this case, r is equal to craft.pos because the Earth's in the origin. But if it was not, this would still work. Now I need to calculate the gravitational force. F equals negative g times me times craft.m times norm r divided by mag r squared. Now I'm going to update the momentum. I feel like I'm missing something. Craft.p equals craft.p plus F times dt. Okay. Update the position of the craft. Craft.pos equals craft.pos plus craft.p times dt divided by craft.m. Update time. T equals t plus dt. What do you think? Let's do this. Python lesson Earth orbit. Okay, and I'm going to run it. Something's not right. Negative. R is... Oh, I got that backwards. Okay, now let's run it. Okay, so one thing I notice, there's a couple things that are really important here. Number one, I think I'm running it too fast. But I think that's okay. Number two, what the heck just happened there? And I'll tell you the answer. I wasn't going fast enough in the y direction, so it started moving down towards the center of the Earth. And I can show you that. Let's just slow this down, play it at half speed. Okay, so it's barely moving that way. It's mostly falling. It's falling towards the center. The Earth doesn't stop it because it's not even really there. Once it gets really close to the center of the Earth, r becomes very, very, very small. And that's going to make the gravitational force very, 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 very large. And at some point, there's a super large gravitational force. It increases the momentum to some super high amount, and then it moves and it's not so far away. So it doesn't come back. It doesn't do what it should do, okay, because it got too close to that thing. And that's just a rounding error. It wouldn't really shoot out like that. Let's fix this by just giving it a larger y velocity and see what happens there. Okay, so it's still not fast enough, but maybe it won't blow up this time. See if it comes back out. See, so it went through the Earth because the Earth's not really there, and it doesn't come back to where it should, which shows me that there is a rounding error, and that's fine. But it does look kind of cool, right? I mean, that's cool. Let's just make it go a little bit faster. 2,500. And I love this process of just picking a value and playing with it. I wanted to get it to actually orbit, so let's make this 45. And then I think, oh, that's pretty good. It might hit the surface of the Earth. It might not. It's going to hit. Oh, it's so close. It went in. But it's going to work. See, look at that. It cut through the Earth. Okay, so we need to go a little bit faster. But it did, you'll notice here, it got back to where it started. That is an important property of the gravitational calculations. If you have something orbiting and the total momentum is 0, which it is because the Earth's not moving, it should get back to where it started. Let's make this go just, let's do that. And let's speed up the rate because I am such an impatient person. I'm like, this is going way too slow. Okay. Oh, that's almost exactly circular, looks like. Oh, it didn't go all the way around. Okay, so I'm going to... Let's make this go for a little bit longer, 3. And let's make this a little bit faster. I want to definitely non-circular orbit just for fun. Okay. That's not going to make it all the way around. That's too fast. Let's do 65. Okay, there we go. Non-circular orbit. clearly non-circular orbit. So we've done the first part. We've modeled the motion of an object moving around the Earth, and I think that was pretty fun. But I want to make a graph to show you the way we can check this is to see. And I didn't change my time interval. I guess I'm a pretty good guesser. So let's go ahead and make a graph of the kinetic energy, the potential energy, and the total energy as a function of time, and then I'll change it to something else in a little bit. So I'm going to say G1 equals graph, X title equals time. I guess it's in seconds. Y title equals E in joules. And then I'm going to put width equals 500, height, can't spell. Height, I can spell, I can't type, equals 250. Now I'm going to make some graphs. So I'm actually going to have three things I'm going to plot here. I'm going to have Fk is the kinetic energy, and it's going to be G curve, color equals color dot red. I always think of kinetic energy as red. And we can even put a label. Watch this. Label equals Ke. And then I'm going to have the potential energy, Fu, equals G curve, color equals color dot green. I think it's the Earth, right? Earth is green. Label equals U. And this is potential energy with respect to infinity. Just have to say that. It's not the actual potential, but that's fine. And then Fe equals G curve, color equals color dot blue. Label equals E. Let's just call it E. Okay, that's good. Now down here, I need to calculate those things and plot them. I should do it before the time, but it doesn't really matter if I have a small enough time step. So K equals magnitude of craft dot P squared divided by 2 times craft dot M. Right? P squared over 2M. U equals negative G times ME times craft.m divided by mag R. Yeah. And then E equals K plus U. And then I'm going to plot FK dot plot TK, FU dot plot TU, FE dot plot TE. Let's run it. Okay, so I think it looks good right here. Number one, as it gets further away, the kinetic energy decreases. That's right. The potential energy increases. It's a negative value, but it's increasing. And the total energy is 0 right there. And then it oscillates back and forth. Okay. Now, the energy versus time makes sense, but what actually makes more sense is the energy as a function of R. So let's do that. And then I think there was a dot, but let's see if I can do this. Okay, so I'm going to change this to R. And then that's it. Down here, I just need to change my plots to mag R. You can't plot R because R is a vector. Mag R. Mag R. Okay, now you'll notice that it's actually going to go there and then come back. So now it's coming back, right? Stop, because the graphs are all coming back the exact same thing they were. They're going to just move up and down this way. And here's your classic plot of the potential energy and the total energy, the kinetic energy. I really like that. There is a thing up here. Let's see if I do this, if I remember. Oops. Okay, I don't know what I did wrong. Glow script. And I go to help. And I go to work with 3D objects. I have to look up stuff too. Everyone has to look up stuff. It happens. Graph options. The basics. interval G curve. Markers equals true. That's not what I want. I thought there was a dot. Dot equals true. That's it. Let's try that. Okay, go back up here. And then I'm going to say, let's just put dot equals true just for the kinetic energy, and then we can add the other ones. Yeah. Okay, I'm going to add the other ones. That's nice. Dot equals true. There's another way to do it too. I've done it the old way, where I did an animated graph, and I'll show you how to do that too later. Okay, so in this case, it's showing a dot at the current location. This is super useful if we're not plotting versus time, right? So now you can see that they are all moving back closer, a lower R value, and that is super awesome. And then it'll go back again down that way and just oscillate back and forth. So, okay, drawing the Earth, making orbits, making graphs, energy is constant. Okay, wait, I should do one more thing. Let's make the time step too big. Let's make it 1,000. Let's just see what happens. Let's see if we can make energy not conserved. Okay, so there, that was pretty bad. But you'll see here that the energy is not conserved. It doesn't come back to where it was. The total energy is not constant. It's changing a little bit. So that is an important check, and that's when you would see that. I probably put dt as 100, and it would probably still work fine. But there you go. Okay, so this code's down below. List to all my other playlists, my videos in this list. If you want to help yourself learn Python, that's what this is for. I hope you enjoy it. I do enjoy making these videos, so I will talk to you in the next lesson.